What type of light is emitted by computers and the screen of an iPhone? Let's set some context. Light sources. We have natural light, like the sun, and also fire, as well as artificial light. There are three main sources of artificial light. The first one, it's not really used anymore. It's incandescent bulbs. That comes from Edison's invention. And today, they are no longer used. Today, we use two other sources of artificial light that are very energetic, and I'm going to talk about them in more detail. They are fluorescent lamps and secondly, LEDs, or light-emitting diodes. To summarize, fluorescent lamps, I would say that it is the neon lights, for example, in supermarkets and everything. And LEDs are screens, car headlights, air lamps, in restaurants, subways, all the screens we see, video advertisements in the street, all of these are things that prevent our brain from functioning properly in the evening, from resting properly, from secreting melatonin also through the pineal gland. So this light emitted by LEDs and fluorescent lamps, unlike the natural light I was talking about earlier that provides a continuous light spectrum, meaning there's a bit of blue, a bit of green, a bit of yellow, a bit of red, just like a nice rainbow. The light from a PC screen or the light from an iPhone screen, even if the color we see can be any color, all the colors you know, actually has an emission spectrum that has a big peak of blue light. And then it drops off. And after that, it's completely discontinuous with just a little bit of red light, but not enough. Not enough to counterbalance the negative effects of this blue light. So to sum it up, it's kind of like the difference between good food and bad food. So, good salad, full of antioxidants, good proteins and healthy fats versus junk food. It's the same here. It's the good light. Even if there's a bit less of it today. Good light versus junk light. In the evening, junk light. Even during the day, today we use screens a lot. That's the light emitted by the computer screen. It's low-quality light that is very energetic. Why? The Einstein-Planck equation, which high school seniors in France can understand, is E equals E nu energy equals H times frequency. Or frequency equals 1 over lambda. Lambda is the wavelength. In other words, to sum it all up, energy is inversely proportional to wavelength. The wavelength is, in essence, you might say, somewhat similar to the unique identifier, or ID card, of a wave, in a way that is, in a certain sense, light is a wave. The light photon arrives with a certain energy, and it's somewhat defined by its wavelength. And the shorter the wavelength of that photon, the higher the energy it carries. And so, the more impact it will have on our retina, on how we function, because the retina is already the beginning of the brain. And there you go, the nervous system is complicated. There are a lot of things that come into play. But all this, to say that blue light, if you look at a rainbow, it's always at the end. Why is it at the end, for example, on the left? It's because the wavelength of blue is the shortest wavelength of visible light. Make it visible. Well, it's the wavelength of the shortest of visible light. So the highest energy, fluorescent and LED lights equal bad light for our eyes, for our circadian rhythm. And it equals high intensity, high energy, and so there are consequences for our biological clock, consequences for our retina, photochemical consequences, because they come in with a lot of energy hitting the cells, especially in children. I'll make another video about that, but kids have pupils that are physiologically a bit wider. The pupil is the window. It's a hole in the eye that lets light in, and the wider it is, the more light it lets in. Kids have a lens in front of the retina. It's a converging lens that focuses the rays of light onto the retina. The retina is like a movie screen that tells the brain we're seeing this image. The lens in adults not only helps to focus the rays of light, but it also helps a bit, finally, to block, to filter blue light and even a little ultraviolet. So naturally, in children, it's actually much more transparent because it's still developing. So to sum it up, blue light in children comes in greater amounts because of that wider pupil, and with more energy because it's less filtered by the lens. It hits the retina with a lot of energy, and therefore on the brain, so to speak.